Welcome back, everyone. This is Professor Herring. In this video, we're going to continue learning about intermolecular forces. We're going to learn about the different types of intermolecular forces that occur and what causes variations within them. Specifically, we're going to learn about ion-ion, ion-dipole, ion-induced dipole, dipole-dipole, dipole-induced dipole, and dispersion forces. Let's begin. We talked already about how the properties of matter depend on the strength of interaction between particles. And we looked at how solids vibrate around each other, liquids flow over each other, and gases move rapidly past each other. And I would just like to clarify that when we're talking about intermolecular forces, we can think of it as the interactions, again, between distinct individual molecules or atoms. Whereas the intramolecular forces, those are the bonds, again. That's looking at either, covalent or ionic bonds. That's within the molecule. Again, if you break a covalent bond, you're changing the identity of the molecule. Whereas if you break an intermolecular force, you're not. And it turns out that intermolecular forces are much weaker than intramolecular forces. This is good. If this were not the case, then our bodies would fall apart as they got close to some other kind of molecule or being. And electrons are not permanently shared within intermolecular forces. This is one of the reasons why they're a lot weaker. Within a covalent bond, we know that the electrons are shared. But with an intermolecular interaction, the electrons are simply temporarily attracted to each other. And also, they don't contain full charges. So in ionic compounds, we're going to get charges of +1, -1, +2, -2, etc. But when we're looking at intermolecular forces, we're talking about the partial positive and the partial negative charges. So intermolecular forces, as I mentioned, are due to the attraction of the electrons within one molecule to the electrons within another molecule. So if we have molecule A and it has some electrons, then they're attracted to the protons present in the molecule adjacent to it. And the strength of these forces depend on the charge of the ion or the dipole moment or the polarizability. All of these are really the same thing. They're just the extent to which the particle has a charge. Whereas a full charge is larger than a dipole moment, which is larger than when it's nonpolar, and we're just talking about the polarizability. It's also related to the distance between the objects. And so what you'll see here is that this looks a lot like Coulomb's law. And that's because it's essentially the same thing. We're just talking, in this case, about force as opposed to energy. And experimentally, we use physical properties such as melting point, boiling point, surface tension, viscosity, etc., to predict the strength of intermolecular interactions. And we'll get some practice doing that. So here's a summary of the different types of intermolecular forces and the factors that they depend on. Remember that Q is talking about a charge. Mu is looking at a dipole moment. And alpha is the polarizability. And we'll talk about each of these in length. For now, we want to realize that the intermolecular forces are additive. In other words, you can have ion-dipole interactions as well as ion-induced dipole interactions, as well as dipole-induced dipole interactions, all within the same set of molecules that we're talking about. And the overall strength of the intermolecular forces is the sum of all those intermolecular forces. These forces are so important to understanding life. Literally, the reason why DNA interacts with proteins to be interpreted and used is through intermolecular forces. All of the interactions within our body are due to intermolecular interactions and the chain of effects that those cause. If we look on the molecular scale, what we see is that proteins are going to be interacting through ion interactions, through dipole interactions, through nonpolar dispersion forces. And all of this helps us to understand why a given protein interacts in a certain way, why it behaves the way that it does. It all has to do with intermolecular forces. So hopefully you'll appreciate this a little bit more in terms of understanding that these things really do matter and really do affect your daily life. So let's talk about ion-ion interactions. This is almost identical to Coulomb's law. Again, the only difference here is we're talking about a force as opposed to energy, but it depends upon the charge of the species and the distance between them. Next, we have ion-dipole interactions. This is where you're going to have an ion, let's say a sodium ion, interacting with a polar molecule. And in this case, it depends upon the ion charge, the dipole moment, and the distance. And we can kind of think of it, if we were to just substitute these in, is that the force is going to be proportional to the charge, dipole moment, and the distance. And I'm going to put x here because it turns out that the power to which the radius, that distance, is raised varies from interaction to interaction. But it might look like the following. If we have potassium ion interacting with the negatively charged region of water molecule, they're going to be attracted to each other. The water molecules surround the potassium ion because that produces a favorable interaction. Ion-ion interactions are part of living systems. Proteins interacting with DNA will form essentially ionic interactions. We also get ion-dipole interactions within living systems, where the charged end of a protein interacts with a positive or negatively charged region of DNA or other proteins or other biomolecules. And the difference here, again, is that these are partial charges as opposed to complete charges. The next type of interaction we're going to talk about are called dipole-dipole forces. And the reason why they're called dipole-dipole forces is because we have two molecules that are polar that are adjacent to each other. Because if it's a polar molecule, then it has a dipole. And so, in fact, you'll find that in all of these instances, the names ion-dipole, ion-ion, dipole-dipole are just telling us about the identity of the molecules or compounds that are interacting. And so it depends on the strength of that dipole moment. The more polar a given molecule is, the stronger the dipole-dipole force will be. It depends on how far apart they are from each other, but then also on the orientation. So if I simplify it this way, if we have this type of interaction, that's not nearly as good as having the interactions lined up this way. And so what we see is with all of these different interactions that positives and negatives attract, and that depending on the distance between them, their direction that they face, and their original polarities, that's going to affect the strength of the dipole-dipole force. It turns out, however, that you can in fact induce a dipole within a nonpolar molecule or atom. So remember how we talked about how the molecules are in constant motion? Well, so are the electrons within them. So at any given moment, on average, the electrons are spread equally throughout their molecule, assuming that it's nonpolar. But at any given moment, we might have an increase of electron density on one end of a molecule, leaving a decrease in the other. And that creates a temporary dipole, which then eventually disappears and comes back and potentially in the opposite direction. These are instantaneous. They're fleeting. They occur for nanoseconds, tiny, tiny fractions of seconds. And they just occur, you can think of it as the electrons are sloshing back and forth. Think of water sloshing around in a bucket. If this sloshing around happens within one molecule, it can force the sloshing of another molecule that's nearby. And we call this an induced dipole interaction. So the initial sloshing within a molecule, molecule A here, has forced molecule B to slosh around as well, and that creates a small temporary attraction. It's very fleeting, very weak, but we'll see that these actually make up for a massive amount of the total sum of intermolecular forces. When we have induced dipoles, we have another term for this. These are called London dispersion forces, also sometimes called LDF. LDFs, London dispersion forces, depend on what's called polarizability and the distance between the species. So if you have an ion that has a fully negative or positive charge, both ions and permanent dipoles can force a dipole to occur, as is illustrated here. What we're doing is we're saying, let's say that we have a hydrogen molecule, it's completely nonpolar. If we bring a nitrogen or sodium atom within the vicinity of it, the positive charge on the sodium is going to attract the electrons towards it, creating a temporary dipole on the hydrogen molecule. If we were to remove the sodium, however, then that dipole would return to normal. We can achieve a similar effect when we bring a polar molecule near the hydrogen molecule. So if we bring water near it, then it's going to pull, or that's reverse. If we bring water near it, it's going to repel the electrons away from the hydrogen or the oxygen side of the water molecule, inducing a temporary dipole. We can achieve the same effect on individual atoms as well. It does not need to just be in a molecule. And it turns out that heavier atoms or molecules, they have more electrons. They're more polarizable. And therefore, the strength of the dispersion forces will increase within them. Dispersion forces contribute to the intermolecular forces within all substances. In other words, every molecule, every compound, everything has dispersion forces. If something has electrons in it, or an electron within it, then it can experience a dispersion force. And again, the reason is because what we're doing is we're taking and shifting the normal polarity, or if it's nonpolar, the normal lack of polarity within the molecule. So let's talk about the term polarizability. I said earlier that dispersion forces depend on polarizability. Polarizability, you can think of it as the ease in which the electrons move around. So remember when we talked about periodic trends, larger elements don't hold their electrons on as well. Therefore, they're also going to be more polarizable. It's easier to move the electrons from one side to the other. And so we could see a trend that as the size of the element gets larger, so does the boiling point. Or in other words, the intermolecular forces, the dispersion forces. And again, another way we can think of polarizability is the squishiness of the electron cloud. How easy is it to make the electrons shift from one side of the element to another? And that will be easy if we have a large molecule relative to a smaller molecule. All right, so let's practice. Place the following molecules in order of increasing boiling point. Remember, we talked about how boiling points are a function of intermolecular forces. When we look at these are all nonpolar molecules. If you didn't see that right away, then you definitely need to review Chapter 7 and Chapter 8 material. From this point on, we're going to assume that you can very quickly and easily determine the polarity of molecules. So these are all nonpolar molecules. Because they're nonpolar molecules, the only thing that matters is the polarizability, which is a function of their size. And so increasing size means increasing polarizability. Therefore, the third one is the smallest, the second one's in the middle, and the first one is the largest. And if you actually look at their boiling points, we see that that corroborates our thoughts here. There's another factor that accounts for dispersion forces, and that's the idea of surface area. If we take the same molecule and just create different isomers of it, remember we talked about how we can have constitutional isomers, and if there's branching, then those molecules tend to be more clumped together than if they are straight chained. And when they're straight chained, we get more interactions between various particles than if they are branched up. There's simply not the same level of surface area that's interacting. And so the more surface area, the more dispersion forces. Let's practice. Go ahead and pause the video and answer the following question. Which one do you think will have a higher boiling point? N-pentane on the left or neopentane on the right? Pause and think about this before moving on. Welcome back. So we talked about just recently that the surface area dictates the dispersion forces when other factors are the same. And so since neopentane has a much more clumped profile than N-pentane, N-pentane has a higher surface area, and therefore it's going to have a higher boiling point. All right, the last few slides here are going to hopefully illustrate for you the important nature of dispersion forces within living systems. We've already talked about how ion-ion interactions or ion-dipole interactions and dipole-dipole interactions exist within living systems, but so do dispersion forces. This is a picture illustrating what's happening in biological membranes. The blue molecule in the middle is a steroid, and the molecules that are surrounding it are imitating what a cell membrane looks like. And what we see is that there's a lot of nonpolar interactions or dispersion forces between the steroid in the middle and the long chains on the left and the right of it. And the steroid, what it does is it increases the stability, the strength of those biological membranes. Without it, it turns out, if we didn't have high enough levels within our cells, then our cell membranes would essentially turn into liquid and we would fall apart. Dispersion forces are also vital for the stability of DNA. So we talked about how in between the DNA you get hydrogen, or well, we'll talk about it, but we're going to get hydrogen bonding. Within these chains, we also have this stacking, and this stacking increases the stability of the DNA double helix because those are nonpolar regions that interact favorably with each other. That's it for this video. Thanks for watching. If you have questions, ask on Piazza in office hours or in recitation. Have a good day.